Inorganic Chemistry 1, Block 1, Stereochemistry and Bonding, Unit 1, Stereochemistry and Bonding in Main Group Compound, Content, Objectives, 1.2 Introduction, 1.3 Vsepr Theory, 1.3.1 Structure of Palladium Chloride, Beryllium Dichloride, 1.3.2 Structure of Boron Trichloride, Boron Trichloride, 1.3.3 Structure of Water, ammonia, and methane. 1.3.4 Structure of nitrogen anion NO3-. 1.3.5 Structure of phosphorus pentachloride PCl5. 1.3.6 Structure of xenon tetrafluoride AgF4. 1.3.7 Limitation of Vsepr theory. 1.4 Walsh diagram. 1.4.1 Walsh diagram for triatomic molecule. 1.4.2 Walsh diagram for pentaatomic molecule. 1.5 D-pi p-pi boron. 1.6 Bent rule and energetic hybridization. 1.7 Some simple reaction of covalently bonded molecule. 1.7.1 Atomic inversion. 1.7.2 Berry pseudorotation. 1.7.3 Lewis acid Lewis base adduct formation. 1.7.4 Nucleophilic substitution reaction. 1.7.5 Nitrogen fixation. 1.7.6 Ozone oxygen cycle. 1.8 Summary. 1.9 Terminal questions. 1.9.1 Reasoning based question. 1.9.2 Short answer type question. 1.9.3 Long answer type question. 1.10 Answer to reasoning based question. 1.11 Reference and further studies. 1.1 Objective. Objective of these units are to introduce you with important basic concepts to understand the bonding and structure of inorganic substance. Prerequisites to understand the offering of this chapter are the concept of valency, dot structure of inorganic molecule, hybridization, and general understanding of structural representation and chemical reaction. At the end of this chapter, you will be able to understand and explain the rather difficult bonding and structure of inorganic molecules. 5.2 Introductions. There are several models and theories. It explains the shape and geometry of molecule. One of the important theory by G.N. Lewis provided the knowledge of electronic structure of molecule. Many subsequent theory built upon the foundation laid by the Lewis theory of electronic structures of molecule. Valence shell electron pair repulsion (VCPR theory) is, is a model used to predict the geometry of a molecules from the number of electron pairs surrounding their central atoms. The theory is also called as Gillespie diholomb theory, after Ronald Gillespie and Ronald D. Holm, who were the main contributors to this theory. Valence shell electron pair repulsion (VSEPR theory). The VSEPR model, which explains the shape and geometry of polyatomic molecule, is based on Lewis' model of molecular structure. This theory predicts the shape of molecule from the knowledge of Lewis dot structure. In fact, the Vsepr theory relies on the tendency of the valence electron pair surrounding an atoms to exert repulsion among each other, and thereby adoption of geometrical arrangement to minimize this repulsion. It is important to note that the repulsion between two lone pairs is stronger than that repulsion a lone pair and a bonding pair of electrons, which in turn is stronger than the repulsion between two bonding pair of electrons. Hence, the Vsepr theory make use of position of different atoms and electron around a central atom. Complete positioning of bonded and lone electrons pair of electrons determine the shape of the molecule. The final shape is deduced by ignoring the position of lone electron pair of electron. Although the Vsepr theory can be applied for a variety of compounds, nevertheless it excellently explains geometry of simple halides of the p-blur element. It is also important to note that the Vsepr model do not take steric factors, that is, bulkiness of substituents around the central atom into account. Following are general rules for determining Vsepr geometry of a given molecule. First, draw the Lewis structure of the molecule for which geometry has to be evaluated. Second, place the lone pair and bonding pair of electron around central atoms. Third, electron repulsion decreases in the sequence lone pair, lone pair, greater than lone pair, bonding pair, greater than bonding pair, bonding pair. If the central atom is connected to a surrounding atom by multiple bonds, then the electron repulsion decrease in the order triple bond, single bond greater than double bond, single bond greater than single bond. Possible common shape for the molecules or ions ABN comprising of central atoms A surrounded by an atom of B are presented in table 1.1. Summary of possible geometry and shape for simple molecules. Molecular formula AB2. Coordination number 2. Geometry bond angle is linear 180 degree, bent 180 degree. Second is AB3 molecular formula. Coordination number is 3. Trigonal planar 120 degree, T shape 180 degree, 90 degree. Trigonal pyramid. Molecular formula AB4. Coordination number is 4. Tetrahedral 109.5 degree. Seesaw shape square planar 90 degree. Fourth is AB5 molecular formula. Coordination number is 5. Trigonal bipyramidal 120 degree 90 degree. Square pyramidal pentagonal planar 72 degree. Fifth is AB6 coordination number is 6. Octahedral 90 degree. Sixth is AB7 molecular formula coordination number is 7. Pentagonal bipyramidal 90 degree 72 degree. Few worked examples demonstrating distribution of electrons to minimize the electronic repulsion in some selected molecules, and the resultant molecular geometry are presented ahead. Note that the bonding pair of electrons, that is, bond pair depicted as shown solid line of flying wedges. 1.3.1 Structure of beryllium chloride. Beryllium chloride is a white color hygroscopic solid substance with chemical formula beryllium dichloride. Beryllium chloride has two bonding pair and no lone pair of electron around the beryllium atom, as depicted in figure 1.1. In order to minimize mutual repulsion, the bonding pair of electrons orient far from each other, which result in linear geometry of the molecule. As per VCPR consideration, the chlorine beryllium chlorine bond angle is 180 degree. The linear geometry of beryllium dichloride molecule. 1.3.2 Structure of boron trichloride. BCl3. Boron trichloride is a colorless gas with chemical formula BCl3. This molecule has three bonding pairs of electrons around boron atom. This molecule assumes triangular planar geometry with Cl chlorine boron chlorine. One angle is 120 degree. The triangular planar shape of boron trichloride molecule. Structure of water, ammonia and methane. Water H2, ammonia NH3, methane CH4. 4 bond pair, 0 lone pair tetrahedral. Ammonia 3 bond pair 1 lone pair trigonal pyramidal 2 bond pair 2 lone pair bent 104 degree. Inorganic chemistry part 1 की figure 1.3 geometry and structural attributes of methane left ammonia middle and water right. Each of water, ammonia, and methane molecule has 4 electron pair around the respective central atom figure 1.3. However, the number of bonding and lone pair of electron is different. Methane with 4 bonding pair of electron has a tetrahedral geometry HCH bond angle 109.5 degree. Ammonia has 3 bonding pair and lone pair of electron. Therefore, geometry reduced to a trigonal pyramidal. Since lone pair bond pair repulsion is stronger than bond pair repulsion, therefore H and H bond angle of ammonia are contracted to 107 degree. In case of water, there are 2 lone pair and 2 bonding pair of electrons which surround the oxygen atom. Therefore, the geometry of molecule reduced to bent shape with HOH bond angle of 105 degree. Structure of nitrate anion NO3 minus. The Lewis structure of nitrate anion is presented in figure 1.4, where formal charge on the anion is not depicted for the sake of clarity. The central nitrogen atom has one double bonded and two single bonded oxygen atom around it. There is no lone pair of electron present around nitrogen atom. Hence, VCPR theory suggests a trigonal planar geometry for nitride ions. Trigonal planar shape of NO3 minus anion. 1.3.5 Structure of phosphorus pentachloride. Phosphorus pentachloride molecule has 5 bonding pair of electron around phosphorus atom. There is no lone pair of electron in central atom. Therefore, Vsepr theory suggests the structure of phosphor pentafluoride to be trigonal bipyramidal. The trigonal bipyramidal shape of phosphor pentachloride molecules. Structure of xenon tetrafluoride XeF4. The Lewis structure of xenon tetrafluoride suggests that there are 4 bonding pair and 2 lone pair of electrons around the central xenon atom. Hence, octahedral geometry for 6 coordinated central atom reduced to square planar in case of XeF4. Limitation. Limitation of Vsepr theory. The Vsepr theory makes general statement about molecular geometry, which is very useful in predicting the geometry of most of the molecules and ions. However, there are limitations to the theory, as the predicted structure does not corroborate with those established by physical characteristics. Characterization in some cases are discussed ahead. IF7 and TEF7 minus are isoelectronic with 7 bonding pair of electrons. IF7 and TEF7 iodide iodide septafluoride and tellurium septafluoride minus are isoelectronic with 7 bonding pair of electrons around their respective central atoms. Hence, VCPR predict pentagonal bipyramidal geometry for both of these structures. VCPR theory does not predict different bond distance for axial and equatorial position in pentagonal bipyramidal geometry. Physical characterization establish that the axial bond of these structures are slightly shorter than the respective equatorial bonds. Additionally, the geometry of tellurium septafluoride in their crystallographic characterized Sol seems much distorted from the predicted pentagon or bipyramidal geometry, as the equatorial fluorine atoms are not coplanar. Second, Vsepr theory successfully predicts the geometry of simple p-block molecule, but it is not appropriate to predict structure of d-block element, d-block derivative. Third, Vsepr theory does not take inert pair effect into account, hence it does not explain structure of molecules derived from heavy element of periodic table. Crystallographic analyses have revealed that a species such as Celerium hexachloride 2 virus, Tellurium hexachloride 2 virus, and Bromine hexafluoride virus possess regular octahedral geometry, which is not justifiable using VSEPR theory. Walsh diagram. Walsh diagram were first introduced by Professor A.D. Walsh to rationalize the shape adopted by a polar atomic molecule in the ground state as well as in excited state. Walsh diagrams are graphical representation depicting the calculated orbital binding energy of a molecules plotted against bond angles. This diagram predicts geometry of small molecules and explains why a given molecule is more stable in certain geometry than the other. Walsh rules states that a molecule will assume a structural geometry which provides more stability to his highest occupied molecular orbital HOMO. Walsh diagram is used to explain the regularity in the structure of related molecules having identical number of valence electrons. For example, water and sulfur dioxide exhibit similar structure. Walsh diagram also explains the change in geometry of molecules with a change in their number of electrons or their spin state. Walsh diagram for triatomic molecule. Simplified Walsh diagram for a triatomic molecules is depicted figure 1.7, which is energy versus bond angle plot. It should be noted that the depicted energy level are qualitative and for actual system should be calculated by or suitable simulations. Molecular orbital level drawn on the left are for the bend configuration with bond angle of 90 degrees, whereas those on right are for linear configuration with bond angle 180 degree. Molecular level for bend geometry, molecular orbital level for linear geometry, 90 degree, 180 degree, HAH angle, figure 1.7. Simplified Walsh diagram for a triatomic molecule AH2. The correlation line joining the energy level on left, right extreme depict the energy level for bond angle theta defined by the angle 90 degree smaller than or equal to delta. Delta is smaller than 180 degree. The plot offers quick comparison of the energy for bend and linear geometry with a given bond angle theta. It is evident that the molecule prefer the geometry with lower HOMO level. 1.4.2 Walsh diagram for pentaatomic molecule. For pentaatomic molecule, an imaginary model AH4 can be considered which can assume a tetrahedral square planar geometry. Methane CH4 and sulfur tetrafluoride SF4 are the real example for such category. For instance, for the formation of methane molecule 1, 2s and 3, 2p orbital of carbon and 4, 1s orbitals, one from each hydrogen atom, get involved in bonding. Above mentioned 8 orbital result in 4 bonding and 4 anti-bonding orbital, out of which bonding orbitals occupy all 8 electrons involved in formation of molecule in case of tetrahedral geometry. Significant overlap between the orbital of carbon and hydrogen is possible, which reduce the energy of bonding orbitals, whereas in the square planar configuration, the extent of overlap is very low, which in turn result in orbital considerably high energy as depicted in figure 1.8. Hence, the methane molecule prefer the tetrahedral geometry rather than square planar or intermediate distorted geometry. Molecular orbital level for TD geometry 109.5 degree molecular level of D4H geometry HAH angle. Simplified Walsh diagram for a methane like penta atomic molecule AH4 D pi p pi bond. Formation of inorganic molecule is different than that of organic molecule in many aspects, one of which is the occurrence of d pi p pi bonds. Generally, pi bond, as in case of organic molecule, formed by lateral overlapping of p orbital present on two atoms such as carbon, nitrogen, or oxygen. Bonding interaction between the two d orbital result in delta bond in inorganic molecules are also prevalent. However, bonding interaction in inorganic molecule can also make use of suitably available d and p orbital at once. When a bond forms bilateral overlapping of p or p star and d orbital present on two different atoms, it is called d pi p pi bond. Such bonds are frequently observed in metal complexes such as carbanion and nitrosyl. A simple example is sulfur trioxide SO3. Main groups compounds such as phosphine oxide and disiloxane can also feature d-pi-p-pi bond. Presence of d-pi-p-pi bonding interactions usually result in shortening of bond length of and planar configurations of involved atom. However, observing such molecular feature should not always be attributed to d-pi-p-pi bonds, as several other factors may also be playing role. Hence, a careful evaluation of electronic and orbital symmetries must be made. Phosphine oxide R3p double bond O offer an example of d-pi-p-pi bond in molecules comprising of non-metallic elements. Figure 1.9. In this case, all the p-pi orbital present on phosphorus are utilized in hybridization and hence not available for lateral overlapping. Empty d orbitals on phosphorus except electron density from filled p orbital available with oxygen atoms. This p-pi bond causes tighter binding of both involved atoms, which is reflected in short both bond distance 150 degree picometer and stability bond energy 544 kilojoule per mole of the bond. Empty d orbital filled p orbitals. D-pi-p-pi bond in phosphine oxide. Bonding in metacarbonyls is classical example of d-pi-p-pi bond, where empty pi star orbital present of oxygen atom except electron density from the filled d orbital of metal, which result in the increase in bond order of metal carbon bonds. Filled d orbitals sigma bond empty pi star electron donating by m. D pi p pi star bond backbone. D pi p pi bond in typical metals carbonyl system. 1.6 Paint rules and energetic of hybridization. Hybridization is a concept of mixing of atomic orbitals of different energy and shape to form same number of new hybrid orbitals of equal energies. Hence, hybridization is the energy redistributions of atomic orbital realized by linear combination of atomic orbitals As the orbital energy are of the order of magnitude of bond energies, it is important tool to determine the structure of molecule. Bend's rules relate the orbital's hybridization of central atom in a molecule with the electronegativity of substituents and was originally stated by Henry Bent as atomic S character concentrate in orbital directed towards electropositive substituents. Student, you must recall that S orbital has lower energy than the p orbital. Moreover, a hybrid orbital having higher S character has lower energy and S orbital like shape. On the other hand, higher p character result in higher energy and p orbital like shape of the hybrid orbital. As the s orbital closer to the atomic nuclei, it stabilizes the lone pair of electrons in the p orbital. Hence, it is logical to say that more stable molecular model would allow the orbital rich in p character for bonding purpose and those rich in s character for accommodating the lone pair of electrons. It can also be stated that electron density available on s-rich orbital is closer to the nuclei, hence less available for bonding. Therefore, electronegative substituents would withdraw electron density from p-rich orbital than the s-like orbital. We can illustrate this using structure and bonding. Phosphor trichloride difluoride. Formation of this molecule involve mixing of 1s and 3p and 1d orbitals to form 5 sp3d orbitals. The 5 orbitals are not identical but can be grouped in a set of 2 axial and 3 equatorial orbitals. The equatorial set is resolved by the mixing of s, px and py orbital, whereas axial set is resulted by the mixing of pz and d orbital. Experimental evidence indicate that the fluorine-chlorine atoms in phosphor trichloride difluoride molecule are situated at axial and equatorial position respectively, which is in agreement with Bent rule. Axial plane. Figure 1.11 Position of substituents of phosphor trichloride difluoride molecule left and geometry of p orbital on phosphorus right. Important implication of Bent rules and energetic of hybridization can be seen in the significant difference in the bond angle of hybrid of group 15 or 16 element as presented in table 1.2. Ammonia hydride of bird first element in group 15 feature a bond angle of 107.2 degree, whereas hydride of subsequent element down the group, that is phosphor, astatines and antimony feature bond angles closer to 90 degree. Similar trend can be observed for the group 16 hydride. Formula and bond angle for group 15 and 16 hydride. 1 Group 15 hydride ammonia phosphor ammonia bond angle is 107.2 degree. Second, phosphor hydride trihydride is 93.8 degree. Third, astatine trihydride is 91.8 degree. Fourth is antimony trihydride is 91.3 degree. Group 16 hydride H2O bond angle is 104.5 degree. Sulfur trihydride is 92 degree. Selenium dihydride 91 degree. Tellurium dihydride 89.5 degree. Atomic size of phosphor, astatines and antimonies are large enough to accommodate 3 hydrogen atoms around them without steric crowdings. Hence, the atomic orbitals of this element do not undergo energy demanding hybridization while formation of respect to hydride. Thus, the lone pair of central atoms in this hydride remain largely on s orbital, whereas s orbital of hydrogen atoms overlap with nearly p orbital. On the contrary, nitrogen being small in size cannot accommodate three bonded hydrogen atoms around it without steric crowding. Evidently, the steric reasons cost much energy in case of ammonia to assume smaller bond angles than the energy required for hybridization. Hence, the atomic orbit of nitrogen undergo hybridization, while formation of ammonia to result in bond angle of 107.2 degree. Further, the shortening of bond angle from ideal value of 109.5 degree and can be explained on the basis of Vsepr theory. Similar argument can explain the bond angle trend of group 16 hydride. 1.7. Some simple reaction of covalent bonded molecule. Inorganic reactions are different than the organic one in many aspects, including their structural feature. Organic reactions primarily involve sp2 and sp3 hybridized carbon center. Therefore, organic reactions usually deal with linear, trigonal plane and tetrahedral geometry. On the contrary, inorganic molecules feature a variety of structural diversity. This poses much concern pertaining to the structural, configurational, and dynamic change in case of inorganic reaction. Therefore, this section discusses two transformations involving structural change in inorganic molecules. Subsequent reactions are of environmental and industrial importance. 1.7.1 Atomic inversion. Atomic inversion molecular spatial rearrangement of atom giving rise to the mirror image product. Usually, the molecule involved trisubstituted nitrogen phosphor atom, that is amine and phosphines, shows such a phenomena. Figure 1.12. It should be noted that atomic inversion in non-chiral molecule yield product identical to the starting substance. However, a disymmetric molecules give rise to a product with a molecular configuration that is a mirror image of that of original molecule. The energy barrier for atomic inversion in case for amine is usually so small that the isolation of enantiomer cannot be affected. Starting molecules mirror image product. Starting molecule mirror image product. 1.12 Atomic inversions around nitrogen phosphorus atom in disymmetric amine and phosphine molecules. Berry pseudorotations. Fluxional Fluxional process are dynamic molecular process that interchange two or more chemical and or magnetically different groups in a molecule. Berry pseudorotation in case of phosphorus pentafluoride is classic example of fluxional process in inorganic substance. Figure 1.13. The Berry pseudorotation is a classical mechanism for interchanging axials and equatorial ligands in molecules with a trigonal bipyramidal geometry. Phosphor pentafluoride is a trigonal bipyramidal molecule with D3H symmetric. Therefore, bond angle FPF and FAPF have standard value of 120 and 180 respectively, where suffix E and A represent equatorial and axial position. In the Berry pseudorotation, angle FPF increased from 120 and angle FPAF decreased from 180 at the same rate, so that the final position of equatorial and axial fluorine atom mutually exchange. Therefore, the conversion of one trigonal bipyramidal form into other occurs through an intermediate square pyramidal transition state. Any intermediate position between complete flip of axial and equatorial fluorine atoms are of higher energy and are not isolable. Symmetry considerations suggest two separate beam for equatorial and axial fluorine atom of phosphor pentafluoride molecule. However, at room temperature, The 19F NMR spectrum offers a single peak for molecule, which indicates that the frequency of berry rotation is higher than the NMR scales. Schematic depiction of berry pseudorotation phosphorus pentafluoride. Two trigonal bipyramidal form of PFI interconvert through square pyramidal transition state. Note that both axial and two of the original equatorial fluorine atom in the extreme left structure assume equatorials and axial position respectively in the extreme right structures. Lewis acid Lewis base adduct formation. Lewis acid is a chemical species capable of accepting an electron pair in their empty orbital, whereas Lewis base is a species that has orbital containing electron pair that can be donated to electron deficient species. Hence, Lewis acid can accept electron pair from Lewis base to form Lewis adduct. For example, trialkyl boron Lewis acid accepts electron pair from amine Lewis base to form a Lewis adduct. The covalent bond between boron and nitrogen atom can also be considered as dative bonds. R3b react with Rn NR3 to give R3b NR3 174 nucleophilic substitution reaction. Hydrolysis or solvolysis is a common reaction of inorganic substance which involves nucleophilic substitution reaction. Hydrolysis of trimethyl chlorosilane to yield trimethyl silanol is presented below as an example figure 1.14. Note that the hydrolysis of a related bifunctional compound dimethyl dichlorosilane is used to synthesize a polymeric silicon material. Water reacts with trimethyl chlorosilane form into trimethylsilanol. Synthesis of trimethylsilanol by hydrolysis of trimethylchlorosilane 1.7.5 nitrogen fixation. Nitrogen fixation is a very important reaction involving conversion of natural nitrogens into which has triple bond between two nitrogen atoms into ammonia. The reaction takes place at ambient temperature, zero point 0.8 atmosphere pressure of nitrogen in the rhizobium bacteria found in the nodules on some plants, roots, legumes. The reaction can be present as follows. Nitrogen reacts with 6 hydrogen to give 6 electrons to ammonia. The process of nitrogen fixation involves enzymatic catalysis, which is not discussed in these books. However, it should be noted that enzymatic processes are highly energy efficient chemical reactions in which various enzymes act as catalysts. It is important to know that Haber's process, an industrial procedure to synthesize ammonia, require high temperature, high pressure, and an iron catalyst. Qualitative comparisons of nitrogen fixations and Haber process will allow you to assess the superiority of enzymatic process which are not yet completely understood. The ammonia produced in above reaction is used by plants for formation of essential building blocks of life such as amino acids, ozone oxygen cycles. Ozone O3 is found in stratospheres in large quantity and keep most of the sun ultraviolet radiation from reaching to the earth by absorbing it up there. Ozone molecule O3 present in the stratosphere photodissociate to yield oxygen atoms. An oxygen molecule O2 abound absorption of ultraviolet photon. Simultaneously, ultraviolet photon of appropriate energy also split oxygen molecule O2 into two atomic oxygen radical O. The atomic oxygen radical O combine with oxygen molecule O2 to regenerate ozone O3. This cyclic process continues to occur in stratosphere and prevent the harmful ultraviolet radiation from reaching the atmosphere. O3 react with radiation to give O and plus O2. O2 react with radiation to give two O radicals. O radical react with O2 to give O3. The above ozone oxygen cycle terminates when an atomic oxygen radical O combines with oxygen molecule O3 to yield two oxygen molecule O2. O star react with O3 to give two O2. The cycle can be disrupted by other radicals such as hydroxide radicals OH, nitric oxide radical NO, chlorine radical Cl, and bromine radical Br. The above reaction involve photochemical disruption and formation of covalent bond between oxygen atom in the discussed chemical species. Summary. This chapter has discussed some important concepts to understand bonding and structure of inorganic molecule. Vsepr theory offers a simple yet very useful concept to understand the geometry of simple molecule. Walsh diagram and bent rules are relatively intricate topics that complement Vsepr theory towards complete understanding of structures of inorganic molecule. Lastly, some important reactions of inorganic compound had also been discussed in this unit. The discussion on selected reaction not merely present the chemical transformation but also touch upon structure, environment, and industrial importance of the same.